figure it out. All right, so this is our continuation of the introduction to digital rock physics. So we had last time around, we had an exercise and you were all supposed to report on it. Basically to pick a formation you're interested in, let's say that you have a reservoir in a specific type of lithology, and go to one of the companies that I know about, but possibly there is more, and figure out what it is that they can offer you. So if you want to actually enhance knowledge about your reservoir with digital rock physics and you want to pay somebody to do it, okay, what is the value that will bring in, because presumably if you're going to actually go out and pay for the service, you're going to have to talk to your manager to approve the bill. And you also have to figure out, well, okay, what is the workload and time scale involved, and is it worth it ultimately? Okay? So part of this exercise is just also see to what is out there, what is right now commercially available, versus if you're actually, most of the time as a graduate student, you're interested in the research side of the things. Once you go and work for a company, that's not necessarily so. But basically, what is there that you can actually pay for, and what it is that you need to do yourself. Okay? And there's always some last top of the line, a research method is not going to be commercially available. You actually have to figure out how to develop it yourself. But if there is some fast and quick answer that you need to get to make your decision, then you might want to go and shop for it. Yeah? So in that sense, I want to make you an educated consumer, okay? So that you don't treat these services as a black box, and that you're also aware of what is out there. So part of this course is just to introduce you to the landscape of what's out there, so you can actually be a better customer for a service like this, if that's something that comes about. So let's just sample a couple of those. Did you complete this assignment? And which company did you?
The FEI.
FEI. So what lithology were you shopping for? Or what type of formation?
So they could do.
What type of samples? Do they do imaging? Do they do simulation? What do they offer?
So you can just send them the core, or you can do it either cuttings and core plots, or those small fracture things, and they will do simulation on it. First, they will take 3D micro CT and 2D SEM. Based on those, you can do absolute and relative probability, porosity, the total organic component, the TOC, the distribution of the minerals. Can I remember all of them?
Okay, so there's quite a bit of measurements in addition to the actual just imaging.
Yeah.
And in terms of simulation, would they do anything for you? Or like permeability based on lattice Boltzmann or anything of that sort? Do they specify which method?
No, they didn't mention which method they use. They also mentioned they can build up a lab for you, so you can do it in your lab.
Okay, so they offer building, customizing the workflow for your needs. Okay. So one thing that is actually quite common, and that's common for any kind of software solution, is that those who are selling you the result of the software simulation are not necessarily going to tell you which method they use to actually obtain the result. And we will actually see as we go forward that when you simulate just even something like just a single phase flow through a piece of rock, it's not necessarily straightforward. The results are not guaranteed. Just applying different boundary conditions can throw off your values by 20% or so. Okay. So when somebody doesn't want to answer your question about the method they use, that's a little tricky proposition. But you should know, sort of coming into it, what situations are. So one more company. Has anybody looked at DGM? Yeah? Okay, so what did you find out? Because this was new for me. I found out about it like last week.
Well, the input is rock. They didn't talk about unconventional, so
okay.
I'm guessing more on the site.
Oh,
And
good for them. That's easy. All right, go ahead.
and they have a wide variety of imaging methods. They have multi-energy CT, micro CT, FIB. They have different things that I don't know about. But the estimated properties, they have also a lot of results. They give drainage and division curves from simulation.
Okay.
They
Do they mention
they
which
don't
method?
state the method.
Okay.
They do relative permeability in 2 and 3 phases.
Okay. 3 phases.
3 phases, that's
Okay,
interesting.
that is interesting. So 3 phases difficult. So 3-phase flow is difficult on 4 scale. So it's interesting that the company offers that.
And they also offer molecular simulations.
Molecular. So MD is up and coming. So they are technically, it seems that they're getting ready for the unconventional market because you don't need molecular simulation in a sense, no? Or rather, you don't have the computational power to do it on a scale required. So they are. It seems that they are gearing up for unconventionals. So there's a question of scale. Unconventionals have cores that are less. A lot of them are less than 100 nanometer. That requires both imaging techniques that are tailored for that and simulation techniques that are tailored for that. In the sense that boundary conditions or anything conventionally applied on micron length scale does not necessarily translate directly to that smaller scale. So basically offering solutions that are also fast enough is problematic because with the smaller the scale, more involved the simulation. So this is something that we will actually talk about more, but I just wanted to give you the flavor of how do companies, and if you're actually interested at some point setting up a company, you kind of have to figure out what it is that you're going to offer. Right. So I hope that has everybody submitted their little contribution online? All right. And again, if you joined the course like today, please do so in the next couple of days. All right, so this is the report. Now, here's the typical workflow before we actually can offer all of these as a company, all of these simulation. One thing that I'm going to start with is an image. And we will actually, let's throw that question right in right now. Based on the sample, so I'm going to pass these 2 things around. Okay? These are carbonates from Texas Pipe Creek sample from one of the PhD theses here in this department in 2008. Okay, so essentially there are 2 samples. They're actually from a similar formation. They're not taken very far apart, but you will see that they're very different. This is welcome to carbonates, everybody. Okay. This one looks like rather tight from the visual inspection. One can see some of the openings, sort of like a buggy style, but like very relatively small ones. Other than that, it appears rather tight. And this one is very open and buggy. So question is, what would I image this with? And what would the resolution be? So that's one of the first things that you have to decide. And yes, you can let the company decide for you, but you should have some idea as well, because you're interested in looking in something, in some process, and depending on what you're interested in finding out versus what the rock actually is, you might have to employ 2 different methods of imaging to obtain the image to start with. So this is just to get your thinking process started. But basically, this is the image. This happens to be actually an artificial image. It's a very small, it was imaged at 4 micro resolution. This is polyethylene, artificial sample. It's a proxy for an oil wet rock, okay? Or it was a proxy in my thesis. And this is, we really have about 100 voxels here, okay? So this is 400 by 400 microns that we're looking at. And this is the input image once you decide what the imaging should be and you get that image out. This is only one slice of it and one small piece of it for schematic. Okay. Before I go in and do anything, I actually have to, if I want to do simulation with it or quantify anything in this image, I have to decide who is who. So my eyes see 2 populations here. There seems to be a light gray and dark gray. I have to know what light gray and dark gray is in this image, that's for one. And then I have to figure out how to separate it algorithmically, which is the process called segmentation. So my eyes kind of do that easily, but for computer, you gotta tell the computer what to do. And there are algorithms, and there's a whole host of problems built into this segmentation, because this is my only view in this scale. So validating whether my segmentation is working well is often looking at it and saying, well, that looks right. Not very scientific, okay? And then it's my word versus somebody else's word, whether that's right. Okay, so that's a scientific problem right there. Nevertheless, we work with it. So once I say I went through that decision making, so this is my pore space that happened to be, there's oil that was doped in there, so that's why it looks darker. And this is the grain phase, so I now have pores and grains. I can now do various things. I can, for a simple thing that I could figure out is like, what is the porosity? What is the fraction of the pore space here that I'm looking at? I could take this space and give it to what's called direct simulation. Okay? So that direct simulation could work either with pore space or my grain space and give me certain upscale parameters. Permeability is the simple one we talked about. And then, or I could just further characterize it and simplify it in some way. One obvious thing is to actually run down some sort of a thinning to get sort of a skeleton of the pore space that makes search easier, especially if you're 3D space. It makes visualization easier. It's also a basis for further simplification in what's called a pore throat algorithm. We're going to get into details of that further. So it's a type of discretization of the space that is called pore throat network. And I could actually do some semi-upscale simulation based on that. Okay. It is quite possible that I actually image the process. And that's specifically easy if you're, for instance, is anybody working with micro models? So micro models are two-dimensional models that you're looking at under microscope. They're quasi two-dimensional in the sense that they have like sort of pillars in space, and your fluid is moving in between those pillars, but it's kind of same in all cross sections, so it's quasi two-dimensional. Okay? And you color your fluids and you look at it under the microscope. Okay? So you have typically a video of the process, which is really beneficial for understanding what's going on. And things are in 2D, so they're much easier to look at than it is in 3D. So you might want to just process that and quantify, well, how did this procedure go? Let's say that you had reactive flow, so some of your pore space is obviously getting larger in places, and there's some precipitation going on somewhere else, so there's tightening in other places, so you might want to quantify that process. Okay? So then in deciding who is an important part, you process that video, and then you can get basically quantification based out of it. So those are some that's some typical for workflow that you want to go. So if you have a process that you have imaged, or possibly at different points in time, then you're going to repeat this workflow and get quantification at each end. Here's essentially the process that I started with, and at the time it was very new. So at the time there was like a whole series of images. There was a fractional flow that was imaged, and it became part of my thesis. So here you're actually looking at the same image that has, this one just has only oil in place in pore space. This one has residual oil and water that displaced the oil. Okay. And there was different fractions of oil and water injected. So figuring out, okay, well now I have 3 phases, find out where they are. So this is now my oil, this is my water, quantify what the saturation was, and what is the efficiency of the displacement process was part of what I did for my thesis. Right now it's a standard procedure. Back when I was a student, there was no algorithm that can actually do this segmentation, and that was part of my thesis, was developing segmentation for this. Okay? Right now it actually looks kind of trivial, but hey, there has been some time. What was not trivial is the images. Images here are extremely noisy. To this day, they're a great test for any algorithm that needs to sustain a lot of noise, because back in the day, the imaging was just starting out, so the images weren't of good quality. Today, this is kind of a laughable image in terms of quality, so if somebody gives an image like that, return it. Well, I couldn't return it, I had to deal with it. Not only that, experimentally, there were some issues and air got in. So here's air, which wasn't me, I wasn't the experimentalist, but air got in, but I actually tested it so I could actually segment some air out. So I had a 4-phase system, whether or not I wanted to do. But what's interesting, this is a tomographic view through one cross section, is I started with oil, and then I injected half pore volumes of water, then 1 pore volume, then increasingly more, all the way to 64 pore volumes of water. That's flushing a piece of rock with a whole lot of water. It's not something that we would be ever able to do in a field. You cannot flush a reservoir with 60 pore volumes of anything, water or not. Okay. So basically, regardless of how much we flush it, there's always residual oil left. Well, that's something that we know about rocks. Yes?
The pore volume is, can you define that?
Pore volume is precisely, so regardless of what your piece of rock or reservoir is, pore volume is how much volume do you have in pores. Okay? So when you're designing, if you want to kind of dimensionalize or non-dimensionalize your results, you're going to say that I injected 1 pore volume, meaning that if I inject a pore volume of fluid into a rock, I should have displaced what's in there. And I should see stuff, whatever I injected, I should see coming out at the other end once I inject pore volume. Because physically I had to have enough fluid to break through. Right? So if you have a reservoir, of course, injecting a pore volume is a whole lot of fluid, depending on the size of the reservoir. So it's not something that is necessarily, 64 volumes is not practical in the field, you can't do that. But basically it's just a sign of how long or how much have you flushed your pore. So basically, regardless of how much you flush, at some point you have pathways, preferential pathways through the rock that form, and you cannot, there is residual fluid that you cannot flush out. So that's essentially what it is. So this is the segmented view of the same picture, so you can see that red persists. You can see that I started out in applied math department. Otherwise, I would have covered residual fluid. I would have colored it green. Residual fluid is typically muddy. But I didn't know that starting in applied math, it was all same to me, fluid 1, fluid 2. All right, so.
Those were 2D experiments?
3D. So we were just looking through one cross section, but it was actual X-ray image.
I was wondering about the second image because I don't see a percolation pattern there.
Right, precisely. So that's my one main problem of doing anything in 2D in porous medium, because there's no percolation path. But yes, there is. It's a 3-dimensional experiment, so it was actually, it's just slightly easier to look at it this way. Here's another scale, so everything depends on the scale that you image. This is fractured sand that was imaged at 1 millimeter per voxel here some time back now with David DiCarlo. This is Hasnain Khan, not Hassan Khan. We have Hassan Khan in the room. So basically this was loaded sand, and there was a fracture in the sand that opened. This is again just one cross section, and it's a pretty bad image. But when you actually pile up a 3-dimensional picture, this is slightly squished. This is the medial surface through that picture, and if I clean it up to medial axis, I can see sort of a conical structure to this fracture that has opened. So that's, the structure is something that is of interest to study. So this is an example of pore scale versus core scale. When we say pore scale modeling or pore scale simulation, pore is that means that I had enough resolution to see individual pores and grains of rock, which was the case here. Okay. Now, what is the type of the imaging and type of the resolution that you're going to need for that depends on the rock itself. Whereas core scale, I'm typically looking at something that is averaged. So in this case, I don't see individual grains of sand. I just see that they're denser somewhere and less dense somewhere else. Okay? So this is the fracture that has opened, basically impacts the density of the sand in that place, so there is not as much sand, so I will see that as a different density. And this is what was done with medical CT on a different scale, and sometimes I might want to image the process or core on both scales in order to gain this. This is all great for research, core scale versus core scale. This is still not field scale or well log scale. So there's still one more scale to jump to the actual applications if your interest is indeed to, for instance, improve well log interpretation. So example research objective for this pore scale part would be that you image both just dry sample or maybe saturated with only one fluid. Based on that, you characterize the rock and you can do some simulation and figure out what your relative permeability, for instance, would be based on that simulation. At the same time, you could do the experiment that could also give you where the fluids are at certain times, so you can have data points to validate your simulation, as well as study it on its own. So it's sort of that often happens in parallel, and at some point you're hopefully having, or you have hopefully developed a predictive method that will give you flow parameters that you need in situations where you don't necessarily have the experiment, so you can actually play scenarios and make decisions. So this is sort of one idea of how to put it together. So just to quickly review, so this is the workflow that I showed at the beginning. We start with this type of image. It's called tomographic image. Okay. The process separating the image is segmentation. Then I have segmented or binary or binarized, and there are different names image. Okay. So here I have different phases. How many phases doesn't matter, but there's a finite number of classes of voxels in there. This can actually then go forward to direct simulation. It could be either of the solid or solid deformation of, or some flow in pore spaces. And then I could have some further characterization. So this object here is called medial axis. The process is skeletonization or medial axis extraction. And this object here where I have a pore and throats and then the neighboring mixed pore, this object here is called pore throat network, and the process is pore throat network finding, and that's then going to semi-upscaled simulation called pore throat simulation. All right, so this is just a quick review. Okay, so why would we go through the trouble? We typically want to characterize fluid and solid phases and processes that we don't necessarily see, so we want to explain them. Okay? This fundamental understanding, you want to do it without oversimplifying geometry. So the whole point of imaging is that geometry is what you see it is. And then you still need to upscale the transport processes and help interpretation on some larger scale that could be core scale or well log scale, like field scale, depending on your application. Okay? Now the reason is that most of the time in well logs we have mixing rules. So things depend, or my properties depend simply on the fraction of the material that is within. Okay? Those mixing rules are then kind of straight lines based on my properties is sort of like a linear extrapolation of some fraction of the, say, pore space that I have. Okay. Reality is much more complex. As I pointed out at the beginning, we have typically at least two bicontinuous phases that are intricately linked in 3D. There's quite a bit of surface area between those two. So there's exchange across that surface area or grain. Depending on transport process, there is more or less of that exchange. And both of those pores and grain, if I'm in the most simple case, both of those phases are spanning my entire sample. So they kind of continuous from one side to another. So they can both transport at their own rates, whatever it is that I'm interested in looking at. That complexity typically is not going to be represented or predicted well by a mixing rule. Just by saying fraction, okay, 60% of this is solid phase. Now tell me all of the properties. We wish it was that simple, but it's not. And because of that, that's basically motivates looking into complexity of the geometry. And where are these phases? What is their spatial distribution? How are they organized in space? How much area do they interact across? So that we can actually try to model this a little better. Okay. And the objectives of digital rock physics review, or rather this course, is to understand the basics of image analysis. What is the uncertainty that goes into it? Okay. Get some practical experience with the image analysis algorithms, because that is the first step to get you on quantifying something. And as a scientist, you typically have to quantify. You have to understand that understanding actually comes from quantification. And you should know where to go if you want to study further or contribute to a particular research area. And you should become, there's more and more digital rock software coming online, so you should become an informed user of that software and hopefully develop some on your own. So outline is of the course is as follows. We're going to first introduce what images and image data types we have, and have some practical exercises in that regard. Then we will move on to imaging techniques and a quick review of imaging techniques that are employed. Then we will start with the image analysis, grayscale image processing, segmentation. How do I quantify once I have segmentation in place? And then advanced topics. And here is where we will actually get into some of the direct simulation methods and so forth as the course proceeds. Okay. All right. How this course came about, so it was first actually held here in Austin. It was my grand idea to put the course together. Back in the day, there was really nothing. Right now, one can actually see courses here and there on the topic. But in 2013, there was none. And together with Dr. Wildenchild of Oregon State University and Dr. Shepard from Australian National University, put together this short course. And 2011, I'm sorry, actually. So that was at UT Austin, and then we had it once more in Prague in 2013. There was one more in 2014 in Wyoming, and I taught this course last time on this campus in 2014. All right, so this is these are the references. If you want very quick reading, just like sort of on the overview for the industry, that is this digital rocks are how to become a core technology from JPT. Review paper, one of the key review papers on imaging, recent ones, though there's 3 or 4. There's this one on X-ray imaging. This is the paper from my PhD work about the polyethylene cores that I showed. And this is the review paper that is easily accessible in Advances in Water Resources on just pore scale imaging and modeling. And there is a book that is available in our reading room from Dr. Blunt on multiple flow and permeable media. But it does overview a lot about the methods, so regardless of just flow focus, there's quite a bit in there. Okay? So those are the references for you to take a look at. All right, so now we will, in the next 20 minutes, start on image data types. Does everybody have a computer or a friend that they can use the computer with? I'm going to start introducing, so maybe we don't get to the exercise, but either today or on Monday we're going to start working on an exercise, and we'll do it here in class. I have posted lesson 2 on Canvas. So we will start, of course, with assuming somebody has taken an image for us. We're just going to quickly introduce some issues around surrounding data types and how images are actually stored, because that's ultimately one of the headaches that we don't want to deal with but have to. Okay? So, quick introduction. So soil and rock samples are routinely collected. SEM and thin section imaging is part of the standard procedure in petroleum engineering, at least, to basically take a number of samples, and then geologists typically go and process them and tell us something about the rock itself. What are the grain sizes, what are the porosity that they see, and so forth. And that becomes part of a well log. Now, of course, there's also well logging where you kind of knock on the rock in all kinds of ways and listen back what it says, so you can have measurement of nutrient porosity, resistivity, and so forth that are accompanying that. Okay. But we can actually see a thin section. You can see this blue epoxy. So epoxy tells me where the connected pores are. And one of the fundamental ways is to just simply go and quantify that. It is quite amazing how much of this procedure is still manual. Trained geologists who are trained to do that actually process things manually. That is in part because of the complexity of the texture. So there has to be a decision maker. It is kind of hard to train software to make decisions. So there has to be a decision maker, that is a geologist, that knows what they're looking at. So they typically, in some sort of semi-automated way, process these images and ultimately give the value. Now, one of the things that amazes me the most to this date, given that my training comes from sort of algorithmical side rather than having patience to sit and look at image point counting. Okay? Point counting is literally dropping a number of points into your image and figuring out which one fell into pores, which one fell into grains, and then a fraction of those in pores gives you porosity. Okay? Assuming that you have a representative number of pores. This is where computers, that's what computers are made for. Right, so automating the process, of course, can go a long way, even if you still need a decision maker to bring some of the decisions. Okay? So we have the routine collection of samples. What we're really after is, okay, this is all and this is all great when it's done in 2D. In 3 dimensions, I cannot have a person process image. Okay? That is possible, though not anymore done, in medical imaging, where I possibly have 14 slices through a grain. Okay? A person can go and look through 14 slices and trace. In medical imaging, you typically trace where the brain is or whatever tissue you're looking at. In petroleum engineering or subsurface engineering, with the complexity, where is that carbonate sample? Who would volunteer to point count 1,000 slices through that piece of buggy carbonate? It's you would, and your PhD would be done 10 years from now. You could possibly go, right? So at some point it becomes prohibitive. And we have to actually have algorithms decide for us, even if those decisions are not perfect. So that's the reality we're facing. Okay? Because ultimately, we do want to find out, a lot of times we find out, well, yeah, my pore space doesn't seem to percolate in 2D, except that it does. Epoxy obviously found its way through 3-dimensional pores, right? So it's connected. I know it's connected. Okay? So I would like to see that in 3D, and I would like to image and analyze things in 3D. Ultimately, we want to quantify things, porosities, volumes, surface areas, you name it, that are based on those images. And then I would like to predict my flow or solid phase properties based on that. Okay? So we would like to also investigate. So the simulation also allows me to investigate scenarios that I possibly have not exposed my rock in experiment. Now, image length scale. Example I already sent through the class. So you have to decide what is the scale of the image that you deal with. One of the first image that is always obtained is seismic survey. That's not the class of the images we're gonna be interested in here. They have some structure to them, but they don't have obvious solid and pore space. And typically, the scale of the image determines what it is that we're looking for in the image. Image itself is just a collection of numbers, so there is a connecting thread to no matter which image we have. Here's another example that has multiple scales. So this is a basalt rock. It has these openings that are on millimeter scale, and it has a matrix that has sub-millimeter and probably micron scale openings. So based on what I'm interested in, I might want to image this rock with multiple resolutions in order to find out the processes of interest. So you have to know what you're looking for. So, and then basically that will determine the level of the upscaling of the parameters that you need to do. Is there a clear way for you to tell, well, how many images do I need to completely describe this rock? That's right now a research area in itself. Okay. What image and on what scale do I need to make that decision? And how many are representative of my rock? That is rock dependent. So there's no prescribed recipe to guide you before that other than your budget and time. Okay? So those are the boundary conditions that you cannot typically argue with or need to graduate in time, right? Which comes down to budget and time again. Okay? So there's certain a feedback loop that needs to be built into whether do I have enough images to tell me what I need to answer for. And then I also need some accompanying measurements. So if I'm not going to do them, I need to have a fellow graduate student or somebody in some research group or some company somewhere measuring property for me so that I can see that whatever I got is realistic. Okay. So we need to validate whatever modeling effort we're doing. Okay. So examples. So this is actually example tracer test through one of the cores that I sent out, the one labeled 1.3, that's the tighter one. Okay. This 2.3, that's not, the Vagi one is not 2.3. That one got mysteriously lost somewhere. So in any event, so this is a tracer test, and this is again where time in seconds is actually commensurate with the pore volumes of fluid injected. So I have to figure out what the porosity of the rock is to figure out what pore volume is before going in. And somewhere around 1 pore volume injected, if the rock is uniform, I'm going to see tracer come out at the other end. Okay. So this is what sort of happens in a normal piece of rock. Even though I inject sort of for some period of time, I inject a constant amount and keep it, and then, so I send sort of a wave through that is just like a square wave, but this is what comes out because rocks has heterogeneities that make my fluid zigzag through. But if everything comes through, then what integrates under this curve is the amount or concentration of stuff that I injected. So it should integrate, if normalized, it should integrate to 1. If everything came out. Now, in this particular case, this is a student, Nara Nair, who did the experiment. So he did one, and this red one was everything as expected. And the blue one, well, he had what's called early breakthrough. Okay. There's some magic pathway or speedway in there, and the fluid zipped through and started showing up immediately. And then there was quite a sort of zigzaggy way from there, so then fluid started getting lost through the core. So it's obviously a little more heterogeneous core than initially expected. So this is an example where I would like to actually image to see, well, what is going on? What is in this rock that actually allowed fluid to break through really quickly, but then not so quickly recover after that?
Where was the concentration measure?
Hmm?
Where was the concentration measure?
This was the lab, so you're actually looking at the lab samples right there.
Yeah, but was it the fluid?
Yes, F1. Yes. So this is F1. I'm sorry. So at the other end, the concentration was measured. Okay. And you're actually looking, they're still staying, the cores are still staying the same as from the experiment. So to explain that, there was an image taken, and this is the second one that actually kind of broke through faster. And when you actually just look at the cross section, so this was the entire thing was imaged with a resolution of about 65 micron. That was not enough to completely resolve. So the very tight stuff. So these are the most open pores. These are the sort of the closed, the very closed or very tight solid. And then the majority of it is sort of microporous or in between. So there's some porosity here that I'm not resolving. Okay. But if there is a highway, I should be able to see it in dark gray, maybe. So one can actually walk through one of these. Let's see if it's gonna show. Okay. Do we see the movie? I don't see it. Okay, interesting. Okay. It shows up only on this. I'm not sharing screen correctly. I'm gonna exit and show and open it from the. Okay. So this is the beginning slices typically have some issues, and I'm gonna speed up. So this is as I'm moving through. And you can actually see a bit of a fracture starting to develop. And it's a very thin hairline. So one has to analyze this a little longer. There was not much quantification done on this image. This was just an example. But this fracture persists through a good portion of my sample. And it possibly connects to whatever was vaggy there, and that basically creates a pathway. Now, fracture is not big, but it's obviously visible, whereas most of the microporous space is not visible. So therefore, it is a much faster flow through than the rest of the matrix. So this is one way to explain what's going on, is simply to look inside and look non-destructively, so that core is still intact. So we observe, again, this is the fracture or this crack that is observed throughout. So this could explain early breakthrough. This is qualitative. I did not quantify. The reality, and we're going to get to it, is that this is a rather thin feature. So it would be actually kind of hard to quantify and actually pinpoint what its actual porosity, fracture porosity is. Now, when you do have enough resolution, you would see individual grains in pore spaces, and this is one of the bad examples from my PhD again. So images don't look this bad anymore, okay? But this is a sandstone, this is a Berea sandstone. So this is an opening pore space, and this is actual sandstone. And this one, I can do a little better quantification in terms of figuring out what the porosity is. And I'm going to keep stressing this. This is porosity of 20%. That is plenty connected in sandstone world, but I'm not going to see a connected path in just one two-dimensional cross-section, which makes it difficult to, if I'm thinking of designing a micromodel that looks like a sandstone, it's not going to be able to have this blueprint because it's not going to connect through. So then the reality of my micro model experiment is that I'm going to have porosity that is, for instance, 60 to 70%, which is not realistic for sensors. I can still learn, but I have to live with that limitation.
What was the resolution of your machine?
This one was 5 microns, 4.93 actually. So that's a decent resolution, and that's one of the common resolutions used for sandstone. That one, for a sandstone, classical sandstone, you can almost go and just say 5 microns should be. Okay. All right. So again, objective of the image analysis is to identify. Segmentation is the crucial process for that. Identify voxels or phases of interest. And further, identify any other individual objects. For that, I need to know what I'm actually looking at. It could be connected, disconnected pores. It could be vugs. It could be fractures. It could be individual minerals. It depends on what you're actually imaged. And you want to quantify the connectivity and spatial distribution of these phases. Are there any key structures? Are there connecting paths across the volume? And you want to find the volumes and areas. And ultimately, you want to do predictive modeling using above information. So this is just a review of that sort of schematic of the workflow that I already talked about today, so I'm not going to spend more time on now. Images are the starting point once somebody gives me an image. So let's look into a little more detail what images are. This is my favorite example. This is an image, and there's 100 by 100 numbers here. When I zoom into that little red portion, this is actually what I see. So I see a matrix, okay, and I see a gray value. It's visualized as a gray value for each number. Okay? These numbers are literally here. This is 220, 215, 210, and so forth. Okay? And it's my job to strike an interface somewhere here, which doesn't look as easy as it does when you're looking from afar, does it? Okay. So this is the typical blurring that is due to the limited resolution. Okay. And the interfaces are not always what they appear to be. But what you're dealing with as an image is really a range of numbers. Now, what type of numbers just simply depends on what type of image you have and what is your scale. The scaling in itself is arbitrary. Okay? So there has been some image reconstruction that has happened, and these numbers in absolute sense mean nothing. They mean a little more in medical CT where they're scaled to Hounsfield units. So there is like something that is CT of air versus CT of water, because there's a specific scaling that is applied. But in a lot of images, there's simply some arbitrary scaling. So in and of themselves, these numbers don't mean anything. Okay? Now, this is an array of numbers. Your screen here or screen here is an array of numbers as well. This is 1024 by 768 pixels most of the time. That's an image as well. If it has color, it's simply 3 separate images that have red, green, and blue values in it. Okay. So for the most part, we look at color as fake. It's really just for our visual enjoyment. And we will deal with just like one image with one set of numbers. And it's important to know how to analyze those. Everything else is really just repeat 3 times over for different color values. Okay, so we're going to continue this discussion on Monday and come ready to work on something. Please install PGE. In these slides that I posted, there's information how to install PGE. In the next couple of slides, so you can download it and install it on slide 22.